We are going to go back to our representation of numbers and just a quick review. Computers are essentially dumb. Okay? We need to tell them everything and rules how to do everything. And specifically, when I want to actually store something in the memory of a computer, I have to have strict rules of how that something is stored, and those rules depend on what it is that I'm trying to store. So if we first tackle numbers, we are used to, as humans, to digital, the system that is depending on 10 digits, which is called decimal system, which has a natural reason why we like number 10. Okay? However, computers don't have 10 fingers. The only thing that they really have is on and off switch. Okay? Electricity is on, electricity is off. So they're really binary. They have 2 digits, 0 and 1. Off and on, and we have to somehow work with that. Now, we tend not to think much about it. We have accepted decimal system as our starting point. Right? However, when you actually think about decimal system, we had that problem of trying to represent number 25 and in the smallest number of coins, assuming that I only have coins of 1 cent and 10 cents. And that's really how decimal system works. It's trying to minimize number of objects, if you will. And it takes objects of 1, 10, 100, so basically powers of 10, and is putting a number together that way. So when I have a number 138, it is 1 times 100 plus 3 times 10 plus 8 times 1, which is what I'm actually representing by 138. And we know precisely that by the position of those that I have hundreds and not thousands. Okay? If I had thousands, I would have to add a 0 at the end. So there is actually a strict position in this lineup of digits that actually gives us the number when we say 138. So 138, we know that 381 is strictly something else. So we know it has to go from one side, right? So when I'm writing, it goes from left to the right. And basically, the rightest most digit is those ones, and then it goes further. It actually extends further. So if I have 138.1, we're still talking about the powers of 10. It's just that I went into the negative powers. So 0.1 is 1 times 10 to the minus 1. 0.1 is 10 to the minus 1. If I had 138.12, I would add this 0.12 is 1 times 10 to the minus 1 plus 2 times 10 to the minus 2, 0.01, yes? So it's still all digital, and it's still all powers of 10. It's just I go positive down to 0, and then I start negative after the decimal point. So we kind of accept that system, and we don't even think about it. But we can translate equally these numbers into any other base, what we call base. And I can actually translate numbers to binary base, and we need to do that in order to store them on a computer. So if we start with integers, one thing that we also need to know is that it has been agreed upon on a computer that this single smallest unit of representation is a bit, which is 0 and 1. And I go in packs of 8 when I'm packing the memory. So my word is 1 byte, which is 8 bits. Okay? So let's figure out how do we represent numbers. So we had this exercise last time when I realized, okay, 25 is 2 times 10 plus 5 times 1, and I can do the same exercise for base 2. I just now imagine I have coins of 1, 2, 4, 8, 16, which are basically powers of 2. And then I basically figure out, well, what is the largest one I can fit into the number? I go with that. And for the remainder, I basically apply the same principle. What is the largest power I can put in? And when I write that down and don't skip any in between, okay, so this means Do not skip any, put a 0 as necessary. My representation of this number is 11001 in base 2, and I denote base here. This is standard thing that we do, so I still denote it to mentally say this is decimal. Yes?
So how do you represent the negative?
We're going to get to that. You're a little ahead of me. So you have to actually reserve a bit in that word that is going to be for the sign. Plain and simple. Okay? So you have to have space for it. And that will, as we will see during the day today, that determines then how large of a number you can actually store. So basically, what is, so just to test whether you were following what I was blabbing about, 0.75 this in base 10, our regular 0.75. What is that number in base 2? With decimal point and everything. What are my powers of 2 that are negative powers of 2? 2 to the minus 1 is 1/2. 2 to the minus 2 is, how many of each can I fit into this number? So the largest one I can fit in is 0.5. Then I have 0.25 left. What's the next power of 2 I can fit in there? 0.25 is the power of 2. It's 2 to the minus 2. So this number is 0.11 in base 2. Did I blow your mind?
Would you say that again? Yeah.
So this is 0.5 plus 0.25. That's
Yes.
1/2 plus 1/4. Those
1/2.
are powers of 2. Those are my coins. Okay?
So 1/2 plus 1/4.
So this is 0.11 in base 2. This number. Okay? Because it's 1 times 10 to the minus 1 plus 1 times 10 to the minus 2. Okay. So the principle is the same. We don't even think about it. We don't think about 0.7. Oh, disconnected. Hi. Let me connect again. I will reconnect in a second. It says 7801. Okay. What? Okay, so now it says I gotta restart. Okay. 7801. It says 7801, correct? Okay. Computer doesn't like me this morning. I'm gonna quickly restart the whole.
Is it because it starts with it's a decimal number that
Yes, so it's a decimal. It's smaller than.
smaller than normal numbers, and so that's why we start.
It's smaller than 1.
1
Yeah.
in binary base. So a decimal normal number in binary base still remains a decimal number.
The number in itself is same. Question is, how do we represent it? How do I write it down?
And if I'm to represent 0.75 in base 10,
It's 0.75. We started from that. I told you I have to start from something. Right?
so in base 10 is 0.75.
So what is, okay, let me flip this on you. What is 0.75 in base 8? What is that number actually? If I actually told you this number is in base 8, it's 7 times 8 to the minus 1 plus 5 times 8 to the minus 2. Are we following?
No.
No.
Too much.
0.75 is in our regular world of decimal system. It's 7 times 10 to the minus 1 plus 5 times 10 to the minus 2. Does anybody disagree with this? Okay? We're used to it. We don't even think about it. These are powers of 10. And I start with negative ones because I'm after the dot. Okay? If I had something here, I would have more of those. Okay? Now, let's say that I told you, hey, who says this is decimal system? How about that we're in base 8? In base 8, my digits are 0 through 7. So it still works. So what is it then? It's base 8. So it's 7 times 8 to the minus 1 plus 5 times 8 to the minus 2. Would somebody be kind to actually calculate this for me? Okay. Now, if I was actually wondering, so this is just me telling you that it's actually base 8 and not base 10. We typically take, if it's not said, you take it as a base 10, right? Now, what is it in base 2? Now I'm looking for powers of 2 that I can fit into the number, okay? And my powers of 2 are 2 minus 1, and 2 minus 2, and 2 minus 3, and so forth. If I have a decimal point there, and less than 1, number less than 1. This is 1/2, 1/4, 1/8, and so forth. Well, it so happens it's a nice number because I designed it that way. That's why it's in my slides. So this is really, this number is 0.5 is my largest power of 2 that I can fit, and then what I have left is 0.25, and by design both are actually powers of 2. So this is 1 times 2 to the minus 1 plus 1 times 2 to the minus 2, which is 0.11 in base 2. So this is my base, and these are my digits. Base, base, digits. Digits, digits, base. So if I just had number 1/8, 0.125, what is that in decimals, in binary system? 1/8, which is 2 to the minus 3. It's 0.125 in the decimal system. What is it in binary system? 001. This one, right? So it's 0 times 2 to the minus 1 plus 0 times 2 to the minus 2 plus 1 times 2 to the minus 3. So it's 0.001. So this spot is precisely for the base to the minus 1. This spot is for the base to the minus 2. This spot is for the base to the minus 3. And my digits are multipliers. Right? Base to the minus 1 is 0.1 here. It's to the minus 1. This spot is for 5 times 10 to the minus 2. Base to the minus 2. And I can switch in between.
So the result of 0.78 in base 8 is 0.95 if we add 7/8 plus
So that's
5
the
plus
actual
0.
number as we think about it in decimal system.
But it's, but it's not equal to 0.75, obviously.
No, it's not 0.75 as we know it in terms of volume,
Right.
okay? Or amount. It's a different amount in a different system. Okay? It's just questions, how do we write it down?
If you were in hexadecimal, would you put like a notation on water?
Yes, so in hexadecimal, everything is the same except that you have digits that can go up to F, I believe, A, B, C, D, F, on top of
If it was a decimal,
15.
if it was a decimal, then you would need to put like F to the -1 or something.
Yeah, this goes further than you want to go today, then just ignore it. Okay? But A dot F is a valid. Okay? A is for 10, F is for 15. So this is my base to the minus 1, base to the 0, base to the 1, right? So this is A, if I was translating this number, which is 10 times base 16 to the 1 plus 10 times base 16 to the 0 plus F, which is 15 times 16 to the minus 1. Same thing. Could go to 155. It's not practical. It's good. Okay.
Well, we need to know.
All of this is not for the test. You can have spring break to figure this out.
Well, we need to know.
And our good reminder is that we will assign a homework on Monday that will be due after spring break. So we'll have these things to mull over during spring break. Yes?
Well, we need to know this stuff for test 2 or test 3.
Test 2, yes.
So I understand like choosing 8 because it's like part of phase 2, but if it was like phase 6, how would we relate that?
So 0.75 cannot be base 6 because 7 is larger than the base. So digits cannot be larger than the base. So that eliminates, but it could be base 9.
How about phase 7?
No, because 7 is the same as the base. So you can have digits only that are 0, 1, up to the 1, base minus 1. In decimal system, 10, base 10, digits are 0 through 9. Okay? In binary system, base 2, digits are 0 and 1. Because the moment you can have this digits that is the base, then you're crossing over in power, right? And then you don't have unique representation. So, because you can shift that to the larger power. If you could do 7 times 7 to the minus 1, that's 7 to the 0. Right? So you can't include base digit as a digit because then you would not have unique representation. Yeah? Okay, now this thing is not connecting me. It says laptop, let's change files. 7801, and I'm typing it in. Okay, let's try HDMI again. Computer doesn't like me today. And now it wants HDMI. Okay, whatever works. I'm not gonna argue with it. Okay. Now let's stick to the binary system. We're actually putting numbers into computer memory. Okay. So if I wanted to put this, so if I actually wanted to put these two numbers, okay, I have to figure out how much of memory I'm going to allocate for a number, especially if I have two numbers next to each other. Okay? Computer has to know where to stop and start the number and read that part of the memory and then interpret as a number. Okay? So we typically reserve 16 or 32 bits for integers. So basically 2 bytes or 4 bytes. Those are my words. I could have a 1 byte integer as well. Okay? And upper limit for something like that, then question is how big of a number can I store inside? So if I had, let's just start with a simpler case. If I had 1 byte of numbers, that's 8 bits. What is the largest, and I'm just storing numbers, binary numbers, what is the largest number I can store in there? For 8 bits. So I have space for 8 bits. I have spot, this is my memory. is the largest number I can fit in?
500.
Well, let's start with this. The largest number is by maximizing all of the digits, right? So throw in all ones in there, yes? So what is this number actually in our translated world decimal system? So this is 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3, 4, 5, 6, 7. Yes? That's the largest number. For 8 bits. If I have only 8 bits of space, it's not much actually. It happens that there is a formula that whenever you have x, some sort of number x to the power plus x to the less power and so forth, this is actually 2 to 1 power up, 8 minus 1 divided by 2 minus 1 by 4. 2 to the 8 minus 1, you all have computers open, somebody can, what is 2 to the 8? 2 to the power 8 minus 1? So I can store only numbers 0 to 255. And as somebody pointed out, I didn't say anything about sign, therefore I'm not storing it. This is unsigned integer. So if I were, what is the smallest number that I can do? 0, just all zeros, right? So 0 to 255 is what I can fit into 1 byte of unsigned integer. If computers worked in a decimal system, and these spots, I was able to have some sort of on-off switches that had representation between 0 and 9 for digits, then my largest number would be 9999999. But computers don't work that way. Okay? Great. So if I actually had 16-bit number, then I would go to the 2 to the 15, 2 to the 14, plus all the way down to 1, which is 2 to the 16 minus 1, and that's this number. It's not a super large number. So that's what 2 bytes give me. What happens if I try to fit in a number that is larger than that?
Split it up and add it.
Computer doesn't do anything. It does some scramble. And basically, that's corruption. That's data corruption. Okay. If you didn't reserve enough memory, let's say that you were designing it and you said, I want 2-byte integers, and then you tried to store 70,000 in there, which is obviously above the limit, who knows what it does? It basically stores an incorrect number. But that's called overflow. Okay. I had a funny story from a friend of mine who was working in, working with Texas Advanced Computing Center. And they were working on speeding up parallel computers. And a lot of times when you have parallel applications, you will have multiple computer cores working on the same problem. And you can design your programs to, at the same time, 50 processors are working, splitting up the same physical problem and working on it at the same time, and then exchanging results and moving on. That's parallel programming. Your computers do that to some extent because they have multiple cores in there, so they're working. But typically those cores are, one of them takes one application and another one takes an entire different application. When I'm talking about parallel programming, everybody's working on the same thing at the same time. So when they were designing their program, they only reserved 2-byte integers for the number of processors. And 2-byte integers go to 65,000. And they were working on a competition to push it over that. And we're getting all these weird memory errors of things just not working and crashing down. Essentially, because they didn't plan for having more than 65,000 processors working on something at the same time. So when they tried to push it to 100,000, the number they were trying to, because everything depends on the number of the processor you're assigned, and if that number is incorrect and incorrectly stored, you get all these mad errors. It took them 2 weeks to figure out that, right? So they lot to go in the unspoken design. You go with something that's working for a long time. But if you haven't planned for, sizing up and you don't have enough space, you will get an error. Computer will continue doing something. It's just that it's gonna build in an error that you have to work with. Okay, so now what if we want to have negative numbers? Then I could reserve, computer has to know that negative numbers have to be stored, otherwise this can be misinterpreted. Right? So then this one is reserved for sign and the rest is magnitude. So if I was working in a 1-byte number, that basically reduces the magnitude of the number. Suddenly I'm going to minus 127 to plus 127 instead of 0 to 255. So I just kind of shifted my range, right? So if I was actually,
Does that mean still have two representations of zero?
yes, and then we're going to get to that in a moment. And then by agreement, we take one away. Two possible representations. So right now, let's just do this exercise. So write down on a piece of paper, give yourself these 8 spots, and let's go back to that 25. How would you store that? And here is how it looked like. How would you fit that into those 8 spots?
Number 25, right?
Yes.
And those 8 spots.
And I have already corresponding things up.
0, 0, 0.
I'm going to start from what I know, and then I'm going to fill it with zeros. Because that's my fixed memory. I cannot chop that down any further. That's my word. So just because I take less than 8 bits to represent that number, I still have to reserve 8 bits for it. Otherwise, I don't know where I start, where I stop. Okay, I'm reading the number. So when we go to NP arrays, we could ask those NP arrays are actually not integer by default, but we could actually ask, hey, let that be 1-byte integer. And then if I ask for 5 of those, then the contiguous 5 bytes will be reserved, and every byte after each other would be one of those array elements. Okay?
So that's number
So I
25.
fill in with zeros up to the word length. Right? If I store this number into a 16-bit number, then I would have 8 more zeros
So that's number 25, the way
in
it's
memory,
stored
computer memory, yes.
in computer memory.
In 1 byte. This is my 1 byte.
And so basically it's 2 to the power of 0 plus 2 multiplied by 0. That's how it works.
These are your powers that are actually 1.
There's an 8 to the power of 1 and a 16 to the power of 1.
So it's really 16 plus 8 plus 1. And then if this was minus 25, and I agreed these numbers to be signed, then there would be a 1 here. But I would not interpret that 1 as the power of anything. I would interpret it as signed. So computer has to know that the number is signed. Okay, computer has to know what is in the memory in order to read that memory correctly. Yes. We're talking about integers only. Yes, decimals are a whole different story. Right. So basically the range, if I shift to negative numbers, my range becomes minus 127 to 127. And then this is a 0, and this is a 0, technically. Whether it's a plus 0 or minus 0, mathematically, we don't care, it's all a 0. So I have 2 ways to represent a 0 in this system. Well, bad design. So in order not to waste one of those is actually simply mapped to minus 128. So if I ask to store minus 128, it's going to be stored like this by agreement. It's programmed into these standards. However, if I go either lower than that, minus 130, or higher than that, 130, I cannot store it in a 1-byte integer, signed integer. Okay? 1 byte or 8-bit. An unsigned 8-bit, then I don't have to reserve that 1 digit for signed, so I can go from 0 to 255. So you can do similar calculations for 16-bit and 32-bit signed integers, like what is their range. I'm just going to give you that range in the end. An upper limit, oops. All right, so now let's move to floating point. I'm not going to spend too much time, just give you like a rough, I'm not going to ask you, hey, here's a number, and ask me how is it represented in memory. We will spend too much time doing that. But let me just tell you how the overall design works. If a real number comes my way, first thing first, I put it into scientific notation. Okay? So I have, if I had 3.75, then I'm going to put 3.75 times 10 to the 1 or so forth. That's my scientific notation. However, I will work with the number converted to base 2. So I can convert that number with base 2, and I hinted how do you actually convert 0.75 into base 2. Right? So you can convert any real number into base 2. And then I will actually, in that base 2, I will convert it to format that is 1 plus some number that is less than 1 times 2 to the t. So my power is not now in scientific notation, it's not 10, I'm using powers of 2. And then I will store p and t in that scientific representation. So basically I convert my binary representation to a scientific version of it with power 2. And then I have a p and t. 1 is always there. P and t to store. And if I had 32 bits to store, I will use 24 of them for this p and 8 for exponent t by agreement. And if I had 64 bits to store the number, which is, if you don't say anything in Python, that's what actually is reserved for the number. Everything is interpreted as a real number in so-called double precision. Okay? Then I'm going to take 53 bits to store this p and the rest for the exponent t. And that also has a sign in there built in. So 1 bit is for sign in each of these. So I don't want to go through the exercise of like, let us see how is this number represented in memory. I just want you to understand that this is where the limitation of how large of a number I can represent comes from. Okay? So my largest number I can do is if this p, which is less than 1, is 0.11, however much I can fit into 53 bits. Okay? And exponent t that maximizes, so I have 11 bits for exponent, one of them is a sign, so it's going to be plus 1, 10 ones, okay? That's my largest exponent. So that basically gives me the size of the number, the largest real number I can put in there, if I just maximize all of those. So technically, largest upper limit, again, we're not going to compute it. Sign takes, just in terms of exponents, sign takes 1 bit. And the largest exponent I can do is 10 to the 23, but it's exponent of 2, which translates to about 10 to the 307 in decimal system. So again, long story short, I do the scientific notation in binary world, and I then for these two p's and t's, I reserve fixed amount of space. Whatever I can fit into that space is whatever I can fit into the computer. If I can go bigger, I can go bigger, but otherwise, I don't. So my limits end up being something like this. So if I have, remember in terms of the smallest number, I can do zero everything out. But there is actually, in terms of a very small number, those are powers to the negative power, right? So my base to the negative power is how I get a very small number. Okay? So I have a limit in how small I can go in absolute value. So I can't do bigger than exponent or smaller than exponent minus 308. So if I do 10 to the minus 408, I'm going to fall into this range in between 0 and that number that is not represented. So I have some sort of a minimum number, positive number that I can do. Then I have some maximum number that I can do when I maximize everything. And above that, I can't store. That's overflow. And then the same thing I have on the negative side. I just put signs to negative, right? And then I have certain we call this underflow in between 0 and the smallest number in absolute value I can do. And then this one. Yes?
Shouldn't the negative useful range be smaller than the positive useful range because one spot's being saved for the sign?
This is give or take. So you can actually, let's take a look at the single precision.
Yeah, I see.
But it's again, these are rounded up some. Okay, we can't show all the digits. So probably yes, but because they're rounded up, we don't see that. Okay. Right? So we have limitations, and yet computers are super useful, right? Okay, so don't forget that. So let's see. Can I represent 4 million as a 16-bit integer? It's about that 65,000 something, okay? As a 32-bit integer, let's see what is the limit for 32-bit integer. I don't have it here, so can somebody quickly try to compute for 32-bit? What would be the 2 to the 32 minus 1 is? 2 to the 32 minus 1.
429, 496, 729.
So does 4 million fit in there? Yes or no? Okay, yes. Then 32767. Yes, I might need to check that because that's actually precisely the limit for my signed integer. Okay, so if you go one more and you have a 16-bit signed integer, you can't do, but you can if it's unsigned, if it doesn't store zeros, okay? So that's the question. That's precisely what the problem is here, minus 32790. If I have 16-bit integer, I can't do it, it's below. Okay? However, if I have an unsigned integer that doesn't worry about signs, then I can do because it's less than 65,000. Okay? And then 60,000. I can in both if they're unsigned, so they don't store the sign. If they store the sign, then I can't do 16-bit. Yeah? Okay. Real numbers. Can I do this one? Let me go back to the limits. Single precision, no. 405 is way above 38. It's also above 308, so I can't do in either precision. Okay. 4 times 10 to the minus 90. I can in double precision, I can't in single precision. And this one? Double precision. Okay. Let's go back. Okay, so it's minus 3 points, so I could still fit it, but barely in single precision. Okay. So careful, because if you then ask computer to store something that cannot fit, it's gonna scramble something. Yes.
Will we have to memorize those ranges right there?
No, you're gonna. That goes on a cheat sheet. I don't memorize, but you have to know about it, and you just quickly look up on the cheat sheet. This is not going to be on this test, but it's going to be on exam number 2. So, very relevant question. Yes.
We get a cheat sheet for this stuff?
Yes. You did not read what I sent out last night. I actually commented on it like a couple of times. Where have you been? All right. We'll continue this story. He's like, what? We get a cheat sheet?